但是这个真没我想象好。我买这个 iPod 的话，绝对是想象的，就是用起来比想象的好。这个就是想象的，充满就买。耳机的真是挺不错的。手表其实好垃圾。
你知道三猫一回是多少？
别考虑了，
我耳朵比较有，
别考虑了，
全是脱落。
不是，就是我收集所有的东西，然后
有些东西没有脱落。
但是就是留到现在。
咱这样带多会长，加头发。而且他就是属于那种很傻逼的人，老太多了。买个包，但是一想，要是说嫌我现在买也。我就买那个打球的那把。现在运动的包吧，放不下我的那个浴袍和浴巾。所以每次我都得是拎着去拎着回，感觉他妈有点。
但唯一的相对128的话，
是，但是不是从才挨个路跑，走的那什么还有大家都瞅，我觉得对，显得有点傻逼。但你一想，傻逼点，回去无所谓，也无所谓。
我想 S 现在就是一个放的，然后我就是看到问题就是你截止了，我得检讨，或者说因为放的来了我才可能会就如果我给你说的话。对啊。
带啥呀？校院那啥。就我这些结果就保险本白痴，也不是好事啊，不好。来了就没吃过了，有点香。都说啥？哎，真是好久没吃。是啊。对，还没吃。下午去校医院，说你可能不信，老美推荐我多喝点热水。没错，没干些性字儿。对呀，他是不是看着我是中国人，多喝点热水，我不是，就好操。还是好。水倒。得给孩子攒钱。哎呀，就是我。 你看速度还应该挺慢吧？
啊，今天零上
我说今天这个我的手台得换手台，我比如说有，我不算东西，你知道吧？根本的。
All right, let's do this. All right, so we will go ahead and get started. Welcome to the 23rd session of EE 7391. So I have some handouts for today. I'll hand those out actually at the break. One of them is the solutions to, in this case, homework number 5. So we have that, and in fact, they're personalized. That's the reason why I have to hand it back to everyone. But basically, this is the solutions, but it also has, if you will, code. I guess it's there. So there's code, and then there's actually, if you will, convergence curves, and so on, if you will, the solutions individualized. So we'll hand that out. I guess I wanted to say a little bit about this assignment because I realized it might have been creating some confusion. I'll go ahead and burn this copy, but I've handed out assignment 6, and I said basically in the table below, for example, write the terms for the non-zero entries. I realize it might be hard to write W11, W12, so if you want, you don't have to write the W. You just write the 1-1 and the 1-2. So for example, it turns out 1-1 goes there. Right? So that's the location for the first weight, as it were. So you don't have to put W11 because that would be kind of painful. But you're going to fill out various different other points along here that are going to correspond to the products of the coefficients with the appropriate data points. That will then result in D11 hat, the first output, the linear output from the resulting filter. So anyway, that was one thing. The other thing is, just to make sure you understand, there's actually 2 things required for this problem. One of the things that's required is an output image. The other thing is a gradient update positions, x's. So you have x's here and you have your output image, and there are 2 different things that go here. Here, you're going to have some image which is going to be smaller than the original image. It's going to have some number of pixels in it, and those pixels are going to be entries of this input image, right? Because you're doing, in this case, max pooling. 2 by 2 max pooling, and again, and you're doing it with a stride of 2. So again, 2 by 2 max pooling is I take this area there for the first one, and I look for the maximum. That maximum happens to be 4. So certainly in the first pixel up here is going to be 4. And then there's the corresponding x that corresponds to the gradient update position, because you have to know where that value came from when you do the updates. Well, that's that position in here, so that's that. But again, this is not the full answer. You got to do the rest. And you're doing the same thing here, as well as here, as well as here, as well as here for these, okay? Now, as we talked about last time, max pooling, you end up only marking particular points associated with that. When you're talking about average pooling, that's entire regions, right? So you end up actually selecting regions, not just one point. The other thing to recognize is whenever you have a ReLU nonlinearity, that will obviously select values. Any values less than 0 can't be selected, right? Clearly from a ReLU. At least if the ReLU is applied first. If the ReLU is applied separately, well then that actually changes it. That actually means that values that are selected that are positive after the pooling end up getting selected. So that's that process. Please engage me in office hours or ask me questions if you do have any questions about that. But I wanted to point that out. Any immediate questions that you guys have? You understand the basic strategies associated with that. That's the reason why then you can use this as your cover sheet, hand this in, and then we'll use that for those 2 problems, those 2 things that you end up filling out. All right, let's continue on. I want to talk a little bit more about batch normalization. I started talking about this as a process to improve the convergence behavior of, in this case, convolutional neural networks. I want to talk about, again, the derivation of that and get into the details. I just started talking about the derivatives when I was there, and that's really associated with this paper. And I guess I'll put this in the notes. This is batch normalization. And again, I'll switch over. And the paper is going to be by Ioffe, Eoff, and Szegedy. So those are the authors. So you can easily, I think, find this paper on the web. It's a well-known paper. And the idea here is we're doing this transformation. So the concept is basically that rather than taking the particular patterns in at every layer, so basically we produce an output which then becomes the input for the next layer. The output of that layer is going to get transformed where we're basically going to remove the mean and normalize out the variance of that particular sample. So we're going to do that for every sample and replace the x's that come in with x hats, okay? That's the idea. And then we're going to have, if you will, after we've done the output of this, we're then going to have y get renormalized back out, okay? So the way to think of this is that basically we're doing a transformation which is going to take out sort of local variations in the patterns. That's the reason why we do this. We're actually taking out variations across a mini batch when we're doing this. And so this is sort of statistics that are run that are basically used to compute these values, normalize out the values, and then we're going to learn the gammas and the betas. And it turns out then we end up learning, we have to do these derivations, the derivatives with respect to the loss function. And that's really what you're asked to figure out is what are these derivatives. And you have an example. This is actually the derivatives that are getting calculated for these transformations, for this particular mean and this variance calculation. And it turns out in your homework, you have a slightly different batch normalization transform. You're saying, where did this come from? I said, well, I created it. Okay, now I haven't written a paper on it. I guess I could generate a paper and say, this is what it is. But think of this, instead of the mean, we're going to use the median for the center, right? Because we can. We can use the median value of a sequence instead of the mean. And then instead of a variance, we're going to use basically the mean of the absolute values of the absolute deviations from x. And again, these two things are kind of robust ways to estimate sort of the scale of a signal as well as the center of a signal, as it were. So these are well known, I should say, in the statistics literature to be able to do these sorts of things. And then, of course, we normalize. We don't have any square roots anymore. But we normalize by our SB, and we shift by our new mu b, which is a median here. And then we do this. So basically, you're asked to compute these derivatives. What is this L? Well, we'll put that in the notes over here. L in this paper, sort of L, it corresponds to the loss function. It's basically equivalent to J sub k, right? So the way to think of it is it's J sub k in the notes that we've been generating here with respect to the class. Now, what you need to do in order to derive algorithms is to be able to compute. We need to compute derivatives with respect to the parameters of this, the batch normalization transform at each layer, because this is going to happen at every layer. And so we need to be able to do this. And what this ends up being is basically the derivative of the loss with respect to particular parameters. For example, when we're talking about this, we need to be able to compute things like the derivative of the loss with respect to the value xi. Now, if you look at this, you're saying, well, that's a partial derivative. That's going to be the derivative of the loss with respect to all parameters that xi depends on. So if I go back and look at the transformation, and again, I'm talking about the original paper. If I look at the transformation, I look at, in this case, xi, where does xi show up in this? Well, it shows up in several places. One of the places it shows up is, actually, yeah, that's the one that has all the terms. It shows up in the definition of x hat, right? xi, we're going to replace x hat with something that depends upon xi. So therefore, the derivative changes in xi will obviously affect x hat. It also shows up in sigma beta squared. So it shows up there because there's an xi there. And it shows up in mu beta. So it shows up in 3 places. So what that means is if changes in xi happen, that means there's changes in xi hat, in sigma beta squared, in mu beta. So what I have is a term, again, coming back to this. What I have then is the derivative with respect to xi hat, that's one of my terms. And then I have dxi hat with respect to the derivative of xi, plus the derivative of the loss with respect to, what's the other one? Sigma beta squared, derivative of sigma beta squared, derivative of xi, plus derivative of the loss with respect to mu. And then the derivative of mu with respect to xi. So now, these are going to, these are things that are going to get propagated, as it were. These are the derivatives that are going to get propagated. These are the things that I have to replace. I have to go in and figure out what these values are, and also recognize that some of these might involve sums, right? I mean, depending upon the nature of the parameterization. Let me do a little better job here. Question mark, question mark. These also might involve sums. And the reason why I say that is, actually, in this case, they don't because it's with respect to xi. But we'll do another one just to be sure that you're aware of that. Now, what is the derivative? Well, how is xi hat related to xi? Well, it's this, square root sigma beta squared plus epsilon. So now I can very easily see that the partial with respect to xi hat with respect to xi is just 1 over sigma beta squared plus epsilon. And by the way, we don't propagate it. We don't go in and then say, well, what's the derivative of the sigma beta squared with respect to xi and so on. We don't do that. So now this value goes there. And in fact, well, actually, let's do the rest. Sigma beta squared is 1 over m sum I from 1 to m xi minus mu beta squared. So again, the derivative of this with respect to xi, well, that just pulls out one of the values. It's still 1 over m, but then I get 2 times xi minus mu beta, and then the derivative of that parenthesis term, which is just 1. And so that, if you will, goes here. And then finally, this one here, if I want to do that, that's going to be mu beta is equal to 1 over m sum I from 1 to m xi. So the derivative of mu beta with respect to xi is just 1 over m, right? Because it's just one of those values. And then this value goes there. So now, if I see I have those 3 terms, if I now look at the resulting expression I have, it's exactly what we just said. It's partial L with respect to xi hat times that, plus the partial L with respect to sigma beta squared times that. That's the value that we get. And then plus this. So it's the sum of these 3 terms. So that's how that ends up getting derived. Now, you might notice there are some derivatives that are like dl d gamma. Well, if we think about gamma, what gamma is in its transformation, gamma actually shows up here in a bunch of yi's. There's m yi's, right? So gamma only shows up here, but it shows up for each yi, and of course there are m of those. So that means for delta gamma, and if I go to this, in other words, I have to think about the dependency in the algorithm if I'm looking at the partial of the loss with respect to gamma, well, that's going to occur for every yi, because that's the only place it appears, but of course there are m of those, so I have to sum across all of them. And then I have the delta, or the partial of yi with respect to gamma. Sorry, not xi. With respect to gamma. And then if I look at what yi is, that was just gamma xi plus, what was it? Their notation. Plus beta. So now, you know, obviously delta y with respect to gamma is just xi. So this guy gets plugged in there. So that's how we end up getting that expression. So there may be sums involved with respect to this because you have multiple terms. But that shows you why, oh, I'm sorry, it's xi hat actually. Sorry about that. It's xi hat. Go back to the PC. The definition is xi hat as opposed to xi. So, so that's the reason why we have a sum. So some of these might involve sums if you have the same parameter multiplying several different terms or affecting several different terms in terms of calculation. So that's how that works out. So basically what this allows you to do now is to basically do the gradients with respect to the parameters so you can actually adapt the resulting parameters of this. And you're saying, well, what parameters are we adjusting? Well, we're adjusting the gammas and the betas, right? We're adjusting these for every layer, okay? So these are sort of layer-dependent things that we're actually adjusting. So that's enabling us then to do this resulting calculation, and as I said, improve the performance. And the main advantage of this, so the main advantage of batch normalization is it allows us to choose large, if you will, similar values of step size. You know, in this case, it's eta, right? So we're able to basically choose a step size associated with this, you know, across different layers and nodes within a layer. And this is the thing. This is really why we're doing it. We're doing this to basically improve a performance characteristic without having to do special tuning of all the parameters or figuring out what those parameters ought to be to get the best performance. But, you know, again, the interpretation is still in a state of flux. Like I said, there are recent papers on this which suggest that this resulting transformation is not about reducing internal covariate shift. Okay, it has more to do with being able to smooth the resulting cost function. So given that fact, I don't necessarily want to say, oh yeah, here's how it plays out. This is the reason why this algorithm works this, you know, this particular way. But it is prevalent enough, I should say, that you know, you'll find some, if you will, frameworks where this is kind of built in. It's hard to defeat, you know what I mean, to take it out because it works so well. It's sort of a feature that people have latched onto in terms of a technique. So it's important to be able to use it and to understand basically what it is that it's doing, at least from a standpoint of a mathematical thing. Like I said, some of these things are actually being worked out in terms of understanding right now as to how they work in terms of a performance characterization. Any questions on this? At least from the standpoint of the homework, I think it's relatively straightforward in terms of what it is that you're doing. I want you to understand the derivation of the resulting algorithm, because that'll help you, if you will, get into variations. Because I think that's what's going to happen within the algorithm space, is we're going to continue to look at variations of algorithms and variations of structures. So being able to go back to sort of first principles and see how these things are built up is important. Yes?
Will batch size make any difference to the whole algorithm?
Yes, yes. So what I wanted to do right now is actually talk about sort of what batch size is and what mini batches are, and actually kind of relate something that we all know well, which is the adaptive filter stuff, to this overall problem to kind of see where, you know, batches come into play. So maybe that's a good transition, if you don't mind, to kind of my topic of kind of batch size. Okay? And, you know, basically there is a choice in the number of, basically the way to think of it is xn, yn pairs to include in a stochastic gradient calculation. So the idea here is, you know, if I think about the cost function, let me talk about a cost, and I'll talk about sum of squared error cost, where basically my j of k is equal to 1 over n. These are all patterns of the sum n from 1 to capital N. And then I'm going to take, since it's the sum of squared errors, it's the Euclidean norm of y of n, the training pattern, minus y of nk. And this is, you know, basically distance squared. This is the training pattern. The training pattern for input xn. And then this is the output of the neural network for xn input, right? Or for the input xn. So I have this, I compute it for every pattern, I then get these and I square this. Now, the point is, if I do standard steepest descent, that would use all patterns at each iteration. Okay, and what that means is basically, you know, I have some Wm k plus 1, that's going to be Wm k minus eta derivative of j of k with respect to the weights in that layer, right? So I'm going to do that. Now, I don't have to do it this way. I can think of this j of k as sort of a 1 over, and what I'm going to do now is I'm going to say b. And then I'm going to say from sum small b from 1 to capital B, and if you allow me to use, you know, b's instead of biases, these are referred to as batches, I'll say jb of k, where this is a batch, okay? And a batch, jb of k, is basically, the way to think of it is, it's sort of, 1 over n divided by the number of batches, sum, and now I have to go sort of n from 1 to capital B, and then I have x of n, sorry, actually I don't want to say that, I want to say y of n, and I guess maybe I'll do it differently. I'll make this, we'll make it p. P from 1, we'll have yp minus ypk squared. This is the pth index of batch B, right? And there is, you know, B is in 1, 2, and so on, up to capital B. So I've sort of taken my problem and divided cost, or split cost, into B batches, right? Now, of course, I don't have to necessarily adapt. So the idea here is, you know, adapt on each batch. So I'm going to basically say Wm, for every layer, I'm going to say Wm k plus 1 is equal to Wmk minus some eta with respect to Jb of k. And then I'm going to, you know, change, you know, cycle through the batches, if you will. Cycle through if you will, B batches. Okay, so that's the idea, is that I'm going to actually now break this up. Now, what does this do? Well, it basically causes B updates in place of one sort of, sum of squared error update, right? So I basically get the benefit of having many more updates looking through all my patterns than just one, right? And now you can kind of see what it is. It's basically, the basic idea is how LMS works, right? I mean, we already said this. We already had this idea with LMS in adaptive filters. We said we could have a cost function with an error surface and get a really good gradient and then go down. Or we could do an average of 1. An average of 1 would just take the current input pattern. This uses not just one pattern, but it uses an average of B patterns, right? So I should say not B patterns. This, except it uses an average of N over B patterns at each step, right? So basically, I still have an average, but the average doesn't have to be N. And if N is large, if N is 20,000, then yeah, I could maybe get away with 2,000 or maybe 200 or maybe even 20. Take 20 patterns. If I take 20 patterns, an average, then I'll do 1,000 updates in place of 1. Right? Where 20 patterns should give me some good descent direction that allows me to go down to the minimum. Okay? You see the point. With LMS would have taken an average of 1, which again you could do. You could do a mini batch of 1. That turns out not to be so useful in neural networks due to the fact that there's two things I think going on. One is the system's nonlinear. And the other is the statistics of your patterns have a lot more changes going on in them than traditional signal processing applications do, as it turns out. So if you want to be aggressive about this, well, you've got to worry about the fact that your resulting patterns have variability in them, and you want to average over some of that. Okay. So this basic idea is basically, the improvement that you got with LMS applied to a neural network problem involving large training data sets. And so we end up using averages, basically blocks, if you will, that are not the entire set of patterns you have in training and are not a single pattern like LMS. It's somewhere in the middle, okay? And again, it's a choice as to how big your batches ought to be. The issue right now is how large is sort of N over B, which could be thought of, if B is the number of batches and then is the number of patterns in your training, this is called the batch size. And this is open to experimentation. There's no one set rule associated with this, okay? And, to actually get this to kind of link up with respect to the adaptive filter stuff, I actually want to go one step further and talk about how this relates to convolutional neural networks, because it's also important to think about it that way. But are there any questions right now up to this point? Everyone understands the basic concept? Yes, question.
So for these questions, you consider about choose the training signal to separate from this different block, and should way to separate the input file, because the training things will be related to. So if you go back to the
okay, I'm trying to get to a question. Yeah, so we have this cost function. We have these batches. Oh, actually, maybe I should. Yes, go ahead.
So for here we know that you change the YN from YN to YP.
Right. So now you're adjusting. Essentially, you're going to minimize across each batch. So you're going to have a different set of patterns each time.
So we should train that. We should have some input signals. So the input signal should be to separate for different block.
Yeah. Basically, you're right. There is an issue here of I have to partition my data. I think this is what you're kind of, if you're getting at, partitioning of data into B blocks. And you have to do this. And by the way, there's a good strategy to use here. You know, you partition data into B blocks. It probably makes sense to take your data and partition into B blocks by randomly selecting patterns, right? So we basically randomize selection. So you don't want to take necessarily the first 10 and the first 100 and the second 100 and so on. It makes sense to kind of randomly select 100 and then randomly select another 100 and then do that so that you select, if it turns out you've got 20,000, then you'll do 100, 200 times to get to 20,000. And then once you've done that, you've set up your Bs, you do this minimization, you should probably randomize the selection again when you do it again, right? Don't use the same blocks over and over because that doesn't really give you much of a benefit. It's probably better to actually randomize the selection to create a set of B blocks, do those iterations, and then go back and then randomize again, select another 200 blocks, which will again randomize over your data. And the whole point behind this is to just do a better job of getting an average gradient that's going to get you down to the minimum point. Okay? So that's another, again, with an average of 1, you don't have that trick. I guess the only trick you have with an average of 1 is you could randomize the order of the presentation. That's all you can do. Here you can actually randomize the mixing of the batches, which is probably what you want to do to make it work better. I mean, it's funny, when I've implemented this, that's naturally what I did. I said, I want to randomize this. I don't want to choose the same blocks over and over again because that seems artificial to me.
Can you have
right?
overlaps between each batch? I mean, the data overlap.
Yeah, and so now the question is, okay, how do I want to randomize? Well, I could have overlaps in the randomization, or I could randomize, with replacement or without replacement, right? I mean, sure. I guess the issue here is no one's really done a formal study to figure out what's best, right? We're kind of now being driven by statistical views of what does it mean when I have a selection of data to try to randomize the resulting selections of values for this gradient calculation. And of course, we understand what randomization does in the world of statistics. We don't really have a good theory as of yet that describes how this randomization affects the gradient calculation or the cost function surface. I think that's an open issue that, again, is probably worth a paper if someone could figure out some formalism to do it. That's the critical thing. Again, you can develop good strategies without an understanding of exactly how those strategies impact your overall performance, but are well motivated by statistical concerns. But I think what's missing right now is, well, how would that choice really affect your performance? If I don't randomize and partition my data randomly every time, will I get a much lower performance or not? Okay, and I think the goal of this is basically to try to, like I said, insert or create opportunities for smoothing when I have them, and that's what this allows you. Right? Without having the smoothing happen within the algorithm, which is what LMS does. LMS smooths by choosing the step size. And again, LMS does that because you basically have the step size, which is controlling your convergence rate. And you're assuming that your data is sufficiently random and you have infinite amounts of it, that you don't need to worry about finite data size. Some of these things are really driven by the finite data size issue in training, which is, I think, a lot of times what drives the overall design.
And for your
Yes.
JBK, for your
Yes, my partition blocks. Let me go back to that. Yeah.
I think it's the sigma is P equals to 1 to B, the N divided by B, not B.
Let's see, N divided by B. Well, all right. So I know I have B batches.
Oh,
I have that,
The next one.
and then this one,
The-
and then B goes there. Oh yeah. Sorry, you're right. It's not the number. But thank you very much. Yeah, that's N over B. Right. The number of patterns I have. Thank you. Right. So I'm averaging over the number of patterns. Thank you. So this is number of pattern. This is basically the number of patterns in batch. Batch, B, small b, that I have. And by the way, it's like, well, why not choose different values of B? I'll have different batch sizes. Why not choose, why not use a measure to select from my patterns and try to make all the batches look the same. I mean, there's all sorts of things you could suddenly think of that would try to do a better job of averaging to get a better gradient calculation. That again, give you ideas and opportunities. We don't really have, like I said, analytic tools that will say, yeah, this is how you sample to get a good gradient, right? This is how you average to get a good gradient. It's kind of driven by the idea that, yeah, averaging is good, and this sort of, using all the patterns in one fell swoop for a gradient is too slow. And I want to make advantage. And by the way, the reason for this is it is expensive to compute gradients, but it's also expensive to compute the outputs. So you kind of want to balance these two things and not spend all your effort in computing outputs to get a slow gradient update. Okay. But what I wanted to do, actually, maybe what I'll do though is we've had enough discussion. I want to talk about how CNNs connect to this, because you can kind of see how, when you put convolution into it, it's kind of like running adaptive filters over multiple data patterns. And then you can see there's even an opportunity there to be able to, have an adaptation, have a batch within a pattern if we wanted to. Anyway, we'll go ahead and pause here. Let me go ahead and hand back the solutions to homework 5. So you have some example code that you can draw from for the homework for this week, which is, I think, one of the reasons why you want to have it. So we'll go ahead and pause here, and we'll come back probably in more like 7 or 8 minutes, since it's going to take me a little time to hand stuff out. So we'll be on a break. So because of the way these were produced, they are ordered according to first name as opposed to last name. So it's kind of mixing up the order. But anyway, the first person who is not here. So it would be Bo Zhang. Xiao Ming Chang. Oh, that's right. Hold on a second. Just two. Sorry, if I can call you back, I want to hand something else to you. Handing out a handout. Sean Wen Zhu. Donkey Ni. Hua Jizhu. Ji Tian. Yeah, these are just solutions, but I got this right. Hai Kui Wang. Han Zhu Tang. Jason. Jay Action. Jihua Li. Jiapeng Yu. Lijie Zhang. Ming Gao. Wu Chen Han. Raldahar. Ru Zhang. Sen Bing. Chen Fei Yin. Shini. Tao Xi. China. Yingshan. Yu Zhao. I got it.
哎，这么看，我觉得有希望。
Yuan Yang.
但是我那个
Yu Dongshan.
close function 没他这么。
Yu Dixia. Jie Yuyan. Oh, see, sorry. Yeah. Oh, say, what's that? Okay. Yeah. Hold on a second. Probably is here. Called it earlier. Xiaoming Chan. Okay, got it. Do this. And I'm sorry.
Sunday.
Sun Bing. Okay, I called it earlier. I know I did, but it's a different ordering this time because of the way my printing printed first names first. Here you go. Uh-huh. Yeah. Yes, the exam. Yes, and I haven't given it back to you. I'll make sure that you get it. I still have it. Yeah.
Professor, I have a question about like in CNN you basically only update the dimensions which is picked by the max pooling, right?
Right.
But for there's another neural network which they do drop out. They drop out certain neurons.
Right.
So what's the difference between? I mean,
Actually, so you can, and you obviously can have them both. If you have a dropout, if you're applying dropout, then for that particular network, so think of it as at the time that that particular version of the network is being adapted, the nodes that are dropped out, it's as if you had no signal pooled for every node that's dropped out. So gradients don't propagate through those nodes. They stop at all signals prior to those nodes, right? Or to every time those nodes. But you're right. It's in some sense dropout, the effect of ReLUs and what's the third thing? Max pooling are all the same thing. They're all a selection process. And they're just selecting different parts of signals to basically propagate for gradients.
yeah,
Right?
yeah, right.
So yeah, and in some sense, when you create code for such things, that's exactly how it shows up. You can think of it as you've got kind of binary indicators in all your nodes that are saying, is this node being used? If not, I do nothing for it and any values prior to it when I'm calculating gradients.
Yeah, because what I'm thinking is for max pooling, you are always updating the fixed dimensions of the data.
That's right. Well, no, you're always updating the values that happen to be maximum for that particular node at that particular output. Yeah.
Yeah. So and dropout is the same. You always update the neurons which is not being dropped.
Correct. That's right.
And
Yeah. I mean, one could be thought of as a selection process on structure. One could be thought of which is independent of signal.
yeah,
Right? That's the dropout. One could be thought of as selection of structure that's dependent on signal, but it's still selection. And then, a ReLU involves the selection of structure which is essentially positive output dependent. So every output that's positive is selected.
yeah. So in other words, if you flatten your data,
Yeah.
especially image data, to a vector,
Yes.
then you use dropout, then basically you can have the same effectiveness as scene. I mean, that's just my guess.
Well, I mean, so these, what do I say? These are all ways to essentially, actually they're interpreted in different ways, but they are all ways to essentially limit the adaptation of parameters, right? And in some cases, they actually limit the input-output relationship, i.e. what values actually get used at the outputs given the inputs that you have. And all of those limitations then mean that the weights have constraints on them, which is what allows you to have many weights. I mean, more weights than you would need to be able to model the system, and yet not have the system just become an amazing curve-fitting device,
Yeah.
right? That has no predictive capability because it's just running random, surfaces through your patterns, right?
Yeah.
So yeah. All right, let's go ahead and we will continue. So what I wanted to do is actually kind of talk about the relationship between CNNs and adaptive filters, because as it turns out, CNNs do impose or do use convolution, as do adaptive filters. So we have been using convolutions all throughout the semester. It's just that the computations are organized differently, and you're going to see via the discussion we're going to do now how things are connected and kind of how the convolutional neural networks actually use block-based computations, but are otherwise employing methodologies that are very similar to those that are in adaptive filters. We're going to talk about the 1D problem only, just to kind of, again, get the feel for it so you have the understanding behind it. And this will also show you the relationship between the gradients that end up being used in, both a system that is convolutive, that is a layer that's convolutive, and a layer that uses subsampling or decimation. And so we'll see both of those things in what follows. So basically in CNNs, they use convolutional operations that are essentially identical to those in adaptive filters. So the way to think of it is adaptive filters are actually versions, there's linear versions of the layers that are in convolutional neural networks. They're just not, you don't have nonlinearities and they aren't stacked on top of each other in a cascaded fashion. But otherwise, these are the same operations. So we can talk about in 1D what a convolution is. And so if we say, and this is the way I'm going to index it. I'm going to say y, well, I have to, again, choose a notation. So I'm going to go ahead and choose, I guess I'll choose I, maybe I'll choose j. Y j of n as being the sum. Actually, maybe I'll use in adaptive filters, I'll use this, I'll do d hat j of n, is the sum, I'll say I from 0 to L minus 1, and I'm going to say wi, and then here's what I'm going to do. This is going to be wik, so I need to have the notation that's going to allow to have the weights associated with this, the weight times x, but in this case, I'm going to say, we'll say j, and I'll say j plus I of n. Now this, I know you're saying is a correlation. But basically that's equivalent to a convolution with an index reversal, okay? But the idea here is this represents basically a convolution over a pattern. So remember, what do I have here? Well, I have my pattern. I call that x of n. My x of n has in it x1, x2, all the way up to some, x, say, well, actually, it's not capital N. It's whatever the length is. I mean, it's going to be whatever the size is. I guess I'll say xl1 of n, right? However long that thing is. And what I'm doing here is I'm actually setting up weights, and I'm saying, okay, I'm going to have a w0 of k. I'm going to have a w1 of k, up to wl minus 1 of k, and I guess I just did it. No, I did that the right way. Maybe I'll do j minus I plus. I'll do that just to allow the indexing to work, because I have to actually go to 1. J is 1. No, actually, I don't need the minus 1. I'm sorry. I have it there. J plus I is fine. So that's what this is. And what I'm doing, of course, is I'm multiplying these guys, multiply, and then I sum. And what comes out, of course, is D1 and K, right? That's my first value. So I pick a 1 there. I do this calculation. And then this guy moves down. And of course, I'll get D2 of n if I shift it down by 1, and D3 of n and shift it down by 1, and so on, all the way to DL1 minus whatever this L is, patterns, right? And actually, it's minus L plus 1, as it turns out. Because that's how many non-zero outputs I get. This is a well-known convolution result, NK. So this is actually shorter by L minus 1 values. That's the thing to recognize, is that this thing that gets computed is shorter by L minus 1 values. And this is what we do. We do valid convolution. Valid convolution patterns, or values. And the reason why we want to do this, and I know you're saying, well, I could zero pat. Or I could start with this filter, maybe further up and use YL minus 1 first and move it down. Well, we generally don't want to do that in systems where we have finite amount of data, because then we'll get these edge effects. We'll get things that adapt, which will kind of emphasize the edges, and you'll start recognizing the pattern because the pattern has some funny, features near its edge that are being somehow selected by the process, by reducing the error somewhat in the resulting training. So we don't want to be able to do that. But you can clearly see this is the same effect that you have with respect to an adaptive filter. And in fact, if we had a desired signal, was available, that was basically, if you will, D1 of n, D2 of n, all the way to DL, L1 minus L plus 1 of n, then we could just use, LMS to update this W0 of k. But the thing, or actually the W0 of k vector to WL minus 1 of k, that pattern, all right? And this would be the 1D pattern. Now, by the way, if we did that, that actually would do something that doesn't happen in neural networks. That would actually adapt the coefficients through the pattern. You see what I mean? We would change the weights as we moved the weights across the pattern, or as we did the convolution across the pattern. The same idea in 2D would be, I would have a 2D image and I would have, say, a 2D set of weights. And as I drag these weights across it, I would be updating it. I would update at every position. at every shift. That's what LMS would do. Now, why don't we do that? We could ask the question, why don't we adapt at every position? We could. The main reason why we don't is because we don't have this idea that adapting through the movement of this pattern across this image would somehow provide better performance. We might as well just accumulate the updates, right? Accumulate the updates, and once we've gone across this pattern all the way through, then we'll update once we have that one pattern. We could do that, okay? That would just correspond, though, to one feature vector. This is one, if you will, input pattern. And of course, how many input patterns do we have? Well, we have not just one image, we have 2 images, we have 10 images, we have 1,000, 20,000 images that we might be classifying, or 20,000 or even larger data sets, speech patterns we're trying to classify. So we don't even do that. And so what we do, so in CNNs, we accumulate gradients over multiple patterns, which basically means, the way to think of it is, if I had my first pattern x1, that would have all this data in it, and then I'd have maybe x2 and you know, had multiple patterns in it. I would have, you know, up to, say, x, what is it? If I have b batches, I would have n over b features, right? In a mini batch, I would actually have all these samples to adapt for my, you know, my W vector, as it were, right? My WK vector. I actually would you know, compute over this entire pattern and then compute over this one. I'd compute a sequence of Ds, which is rather large, right? I mean, it's the idea where I would actually take the data and I would actually take it, you know, multiple patterns end to end and apply a filter to all the patterns to compute all the outputs. And only after I consumed N over B patterns would I even update the dates, the weights once. Does that make sense? And then update this WK to WK plus 1, right? So I actually am consuming a lot of data for my given resulting, you know, convolutional pattern, right? I'm not actually taking just, you know, the way to think of it is I'm not taking just one signal, right? I'm actually taking, you know, one of these patterns as a signal and a second one and a third one and a fourth one, and you know, I have however many values in my mini batch that I'm actually using to generate these sequences. So there is a lot of averaging happening on a mini batch. So what this means is the result is there is gradient averaging even over a what's called a mini batch, which, you know, and it's because of the fact that, you know, the dimensionality of the signal has now been stretched out, right? I've in some sense created a new signal in either time or in space, which is huge in terms of the resulting weights of my filter that I'm trying to compute. So my impulse response then is updated in a way which has a lot of averaging with respect to the gradients that are being calculated. I think that's the reason why mini batches are so successful here. It's because, you know, even for, say, 20 patterns, I've got a lot of signal samples for which my convolution operation can now be estimated. I don't need to have all the patterns in my data set to be able to compute that convolution. And what that allows me to do then is to have lots and lots and lots of convolution operations, which is what these systems eventually have. They have layers of convolution operations that are each being adapted on these patterns where you have a lot of this overall data to be able to do the averaging. So now, by the way, what does that mean? Well, it means that the update for WK plus 1 is WK, you know, and you can think of it as plus a mu times the sum of an E, it's an EI, you know, over one pattern for one input pattern. You know, even if I did that, it would be I from 0 to L1 minus L plus 1, EIN times X, and I guess I'll say XI of N. And again, I only have one of these, so I could say for my first one, for the first input pattern, it would be this, right? And I'm just writing down the LMS version, where again, these are the shift input samples in X1, the first pattern. And these are the errors associated with those shift input patterns. So I'm doing exactly what I would think of, and again, I'm going to have maybe not mu, but an eta. I'm doing exactly the same thing as I would. Now, by the way, how are these computed? Well, these are back propagated. Back propagated from, subsequent layers. But it is exactly this calculation. This is exactly what you're doing. So in some sense, what you're doing is a version of an LMS adaptive filter where your gradients are being computed from, as I said, things that have happened further on in the resulting network. And then, of course, I'd index the pattern, and then I'd go to pattern 2. In other words, I'd take X of 2, and I'd do the same thing. And that would actually be doing, like, for every pattern. Or I could do collections of patterns. So what I could do in a mini batch is kind of WK plus 1 is equal to WK. I have the sum across the convolutions. And then I have P, XI, P. And then I have the sum across the mini batches, right? So eta over NB, sum P from 1 to NB, right? It just averages. This is the mini batch. And this is the convolution operation. But that's what I'm doing. I'm doing that exact computation with respect to this one particular node and this one particular network, right? And so that's how I'm able to do this computation for one particular for one particular output given one particular input and all these errors. This is eta, and this is my averaging over the mini batch. Now, the question is, what happens when you do pooling? So, question. How does pooling affect adaptation? And actually, I'll ask the same question at the same time. How does ReLU affect adaptation? Well, in both cases, and actually, as we just had the conversation, how does dropout affect computation or adaptation? In each case, it's basically setting certain errors to 0. Okay? Now, by the way, it's also setting certain outputs to 0 too. Right? Obviously, certain outputs happen to be 0 as well. But in terms of the update process, it sets errors to 0 because those outputs no longer depend upon the errors. And certainly, with the pooling, what we're doing is we're simply doing a selection. So, if we're doing pooling, which is kind of the simplest type of pooling, is what's called stride convolution. Stride convolution is basically using, every, say, every second, every third, every fourth sample of a convolutional layer. So what this means is, of course, rather than, if I go back up here, rather than having this as my computation, just a moment, there we go. Rather than having this as my computation, copy. So normally I would say it moves down, but now I can move down 2 samples, 3 samples, right? I could do, I don't have to move the same number of samples each time. I could move this down, and so I could basically build a decimated output layer or output signal that has, if you will, instead of, what is it, L1 minus L plus 1 samples, it's that many samples. For example, for 2, right? So I basically reduce that, and what that means then is when I compute the gradients, I'm going to take every other input vector. I'll take this input vector and that input vector and that input vector. I'll skip the input vectors to do the updates as well. So that'll simply decimate the resulting sum. So now my update is not going to be every sample. So this update will now become, actually grab it fully. So this update will now, be, if you will, 0, 2, 4, right? Because I'm only getting every other error. So it just simply reduces the number of errors used in the gradient computation. Okay. Now, the only thing is, and by the way, this is kind of the issue. If you use stride convolution, this is like sort of a regularized pooling. It basically says, let me take every other sample, or let me take every third sample. If I did max pooling, I have to keep track of which one of the values that is the maximum that I'm going to keep around. So my indexing isn't nice like this. It's not every other sample, not every third sample. It's whatever this maximum would be across this, which makes it kind of less, pleasant in terms of computation, some bookkeeping. But it's funny, people have looked at pooling. Pooling was a fairly active area of research, I think until sort of dropout became popular, and then everyone focused on dropout, stopped focusing on pooling, just because of, opportunity costs. Hard to focus on everything all at once. And then people started looking at just simple, decimation, the so-called stride convolution or decimation. And they found, decimation works about as well. So, you'll find these options there. I think the one advantage of max pooling over other pooling methods is it is still a subsampling, which kind of reduces the number of calculations you have to do. So that's good. But this business of stride convolution actually reduces the bookkeeping associated with the decimation. So that's, in some sense, even easier to deal with. So this is a way, if you will, to reduce the number of errors used in the gradient computation, which then, of course, reduces it reduces two things. It reduces overall effort. But the other thing it does in doing this, and by the way, this happens because you're reducing the number of outputs too, right? I mean, it actually reduces the number of outputs. The other thing it does is it avoids the explosion of the number of outputs. And I think I had mentioned this previously. I want to make sure that you guys understand this. Typically, even when we're doing things like image recognition, we might start with one image, as a pattern. The pattern is basically one image. But then we'll expand it out to multiple images in the second layer, right? So I have multiple images at this layer. So each one of these will have an associated pattern with it. And then, so these are convolution operations. These are convolutions. These are 2D convolutions, small number of weights. But notice that I've gone from 1, say, to 4 from my first to second layer. And then if I go from 4 to 8, which is a possibility, right? I might have even more images at the next layer. Then what I'm going to have is, of course, fully connected, right? So each one of these connections is going to have its own convolution operation, right? And so I'm going to have a lot of filters and a lot of channels as I start going up. I'm going to have a lot more pixels. You know, this is why I might want to do at this point, you know, a max pool, so I can make these images smaller. Okay? I can make essentially smaller images, which reduces the number of signal samples. Because I can't simply have a system that constantly grows the number of signal samples. Okay? And even if I don't do this, there are architectures which basically keep the number of images the same. So if I have, say, 4, I might have 4 and 4 and 4. So I don't grow the number of images. But even so, that doesn't help me either. I still need to shrink down the number of pixels that I have. And I do that through a max pooling operation or some sort of decimation operation. I guess maybe I'll say this. At this layer, I'm going to do decimation, which means either max pooling or average pooling or stride convolution. One of those three, or other L2, I can do other ones, which is going to reduce the smaller images down. So again, I'm getting down to, you know, a number of outputs, which is going to be small, because eventually I want to compare this to a small number of samples in my resulting input pattern, say in my classes. So I need to be able to do that. Does that make sense? So that's the reason why I want to be able to do this decimation. Now, decimation is not a regular operation unless you do the stride convolution. So that will, you know, if you will, make the coding different. But what I claim is it is basically just choosing or selecting different errors that you then backpropagate. So hopefully this gives you some sense for what it is that when these codes are designed. And like I said, you know, in the problem that I've given you, I've actually kind of reduced it down to even simpler scenarios where I've said 1D convolution. So you've got 1D convolutions that you're doing here with respect to your patterns. This actually results, this cost function results in an algorithm which actually, you'll find the solution for what this derivative is in homework 5, so take a look at that. And then doing the fact that we are using convolution operation with, stride convolution, then you actually don't even have to keep around the selection process. The stride convolution actually makes that easier from the standpoint of it's basically a decimation process on your resulting error signals and when you're doing your calculations for your gradients. So this again makes it relatively or more straightforward. You know, the only thing that happens in 2D is that you have more indexing. Okay? And the only thing that happens when you do max pooling is that you have now values that you have to keep track of in terms of the locations that you're going to use for the backpropagation. But otherwise, the concepts are there. So please take a look at this. Come to me with questions. I may say a little bit more about this. I mean, it's possible to actually show the resulting coding relationships here, so I may have some things to say about that. I did want to say one other thing, though, which is I did hand out another handout with respect to the solutions, and you want to get this for those who weren't here or the distance students. Basically, again, I pulled a page, a couple pages from Principal Component Neural Networks, Theory and Applications, this very nice book by Diamantris and Kung. And this basically describes, again, in a small amount of language here, don't need very many words to do it, what principal component analysis is. And this is also the subject that we're going to dive into, this and ICA. We're going to start this next time. You might have heard this before, and again, you might have heard it as a tool. Somebody says, you know what, PCA. Use it, because it will help you reduce the dimensionality of your data, right? Because guess what? Images are large, and PCA is a way to funnel your data down from large to small. Well, PCA is a well-understood problem. And again, the algorithms that you use for PCA are ones that are related to adaptive filters, okay? But more importantly than that, you might have heard of techniques which are called initialization by autoencoding. Autoencoding is this idea where you take a neural network where you have the input pattern, and the input pattern appears twice. It appears at the front of the system, and it appears at the end of the system. You're saying, well, what is it at the, you use this, you train the system to learn the input pattern at the outputs. So it's a technique to try to match the output to the input. Now, you might say, well, that seems strange. Why would I do that? Well, if you constrain the network so that the system has a small dimension on the inside, then what you're doing is a dimensionality reduction. You're taking a signal, reducing its dimension down to some layer in the network which has a small number of signals in it, number of samples in it, and then you're expanding it back out to estimate the original pattern again. And if you can do that, then you can kind of think of the first half of this pattern, or first half of this network, as being an encoding technique, which is like an initialization method. That idea comes straight from PCA. So in fact, PCA is not only, a method that you can apply to reduce the number of patterns, it's actually the inspiration for the initialization technique that people use. So it's actually embedded kind of in the process of kind of initializing these networks, as people have chosen to do at times. So that's the reason why it's an important concept. And it's a simple technique that you can train on using a gradient method. So we'll see how these algorithms work. And it has applications elsewhere. So like if you want to build a system to listen in certain directions with microphones, you use PCA. It's actually a very well-known technique for doing that. And then you say, well, what's ICA? Well, ICA is PCA with a non-quadratic cost, kind of like what neural networks use. So we'll get to this idea. So anyway, we're going to start that next time, but I wanted to have a handout to kind of give a framing for the problem, so you have that. We'll go ahead and stop here, and we'll pick up next time. Please do dive into the homework. We've talked about everything pretty much needed for the homework, so dive in and bring your questions. Thank you very much. Hold on a second. Let me get something up here. All right, he's already got it. Yes.
For this question, this
Yes.
LI.
LI, yes.
The LI is what's meaning because
Oh, this is the number of samples in the input pattern. Actually, I should have said L1. I mean,
Yeah.
it's L1. It's L1. That's the pattern. Yeah. Thank you. Yep. All right. Thank you. Yes.
For average, how do we play as